Welcome back to this explainer. Let's jump right in, because today we are looking at something that is quite literally dictating the economics of the entire gigafactory landscape. For decades, battery production has basically been held hostage by this massive, energy-hungry bottleneck, the traditional wet coating process. But there is a huge shift underway. The industry is moving away from that legacy method and towards something called Dry Battery Electrode manufacturing, or DBE. Today, we're going to unpack exactly how this shift is playing out. We'll look at the technical framing, the projected advantages, and the very real engineering hurdles that still need to be cleared.
So, here's our roadmap for today. We'll start with Section 1, the wet coating bottleneck. Then 2, enter the dry process. Section 3 covers illustrative manufacturing advantages. Section 4 tackles the precision gap. And finally, Section 5, market and regulatory impact.
All right, Section 1, the wet coating bottleneck.
To really understand why the industry is so desperate to change, we got to look at the legacy method. Traditional wet coating relies heavily on hazardous solvents, specifically one called NMP. And to evaporate that solvent after coating, these factories need massive drying ovens. I mean, picture an oven half the length of a football field, and it's just running constantly. It's a tremendous energy drain. On the flip side, dry electrode processing is completely NMP-free. It eliminates those gigantic ovens entirely, giving you this drastically simplified flow.
And here's exactly why that traditional method is such a major bottleneck. The conventional wet slurry process literally forces manufacturers through 4 incredibly cumbersome steps. First, you're mixing materials with that NMP solvent. Second, applying that wet slurry. Third, forcing everything through those massive, energy-intensive drying ovens we just talked about. And finally, you have to run these complex, super expensive recovery systems just to safely handle and capture the hazardous NMP solvent. It's heavy, it's slow, and honestly, it's just incredibly capital intensive.
Moving right along to Section 2, enter the dry process.
Take a look at this quote because it brilliantly illustrates where the market is actually heading right now. For years, dry battery electrode, or DBE technology, was viewed as this sort of holy grail that was kind of locked behind Tesla-exclusive hype. But that's transitioning right before our eyes. It's increasingly being viewed not as some niche experiment, but really as a mandatory baseline standard for the gigafactories of the future.
So the core mechanical change at the heart of this whole shift is actually elegantly simple. Just stop using the liquid. Dry processing is designed to entirely eliminate the use of that hazardous NMP solvent. And by removing it from the equation, well, you completely eliminate the need for those evaporation stages and the solvent recovery systems. You're quite literally taking the liquid and the baking right out of battery making.
Which brings us to Section 3, illustrative manufacturing advantages.
Now, before we get into the numbers, just a quick caveat. These performance and cost claims are still subject to real-world manufacturing scale validation, so definitely treat them as projected outcomes. But even as estimates, they are absolutely staggering. Industry literature points to a potential reduction in production energy demand of up to 80% compared to traditional wet lines. 80%! When you aren't powering 50-meter-long ovens 24/7 to boil off solvents, your factory's energy consumption just completely plummets.
And that energy advantage? It cascades directly into the economics of the battery itself. If this dry process scales successfully, illustrative industry estimates are pointing to total cell cost reductions of over 9%. Now, in a high-volume, historically low-margin business, a near double-digit percentage drop is a total game-changer. For us as consumers, this is exactly the kind of manufacturing leap that's required to finally drive down the cost of electric vehicles to actual mass-market parity.
But it's not just about unit costs. It's about the physical real estate. By ditching the ovens and those solvent recovery systems, the actual factory footprint can potentially be cut right in half. As our source notes, in an era of soaring energy costs, especially in regions like Europe, this isn't just a nice-to-have green eco upgrade. Having your factory size is literally a fundamental survival strategy to keep gigafactories economically viable.
All right, Section 4, the precision gap.
Of course, nothing is ever simple in advanced manufacturing, right? The main hurdle blocking mass adoption right now really comes down to this one concept: homogeneity. Basically, this means achieving a perfectly uniform dispersion of all the battery components at extremely high speeds, completely without liquids. Think of it kind of like trying to perfectly mix flour, sugar, and baking powder together without adding a single drop of milk or water to bind them. Getting that flawless, even mix in a dry powder state is currently the holy grail for manufacturing engineers. So how exactly are they bridging this precision gap? Well, large-scale commercialization is still very much an active battleground, but engineers are starting to crack the code. By utilizing things like polar polymer binders and thermal-assisted processing, they're actually finding ways to make these dry powders adhere. Essentially, using specialized polymers and really precise heat, they can bind the dry materials together securely. It creates this sort of structural glue that completely bypasses the need for any liquid solvent.
And mastering this dry process isn't just about today. It's strategically vital for the entire future of energy storage. If you look at next-gen architectures like silicon-rich anodes, DBE improves material loading capability. And for those highly anticipated all-solid-state batteries, it offers incredible architecture flexibility. So mastering solvent-free processing isn't just a trick to make today's batteries a bit cheaper. It's really the required manufacturing pathway to unlock tomorrow's lighter, safer, and longer-range battery tech.
Which leads us to our final part, Section 5, Market and Regulatory Impact. We really have to look at how this manufacturing shift intersects with global policy. An MMP-free process is fundamentally designed for regulatory alignment. Now, we shouldn't imply that this guarantees some sort of automatic official certification, but removing hazardous solvents absolutely strengthens a manufacturer's compliance posture. It perfectly aligns with aggressive emerging frameworks out there, like the EU Industrial Accelerator Act, the new EU battery regulation requirements, and even future initiatives around digital battery passports.
The really major takeaway here is risk mitigation. DBE strategically decouples battery manufacturing from all the environmental and regulatory headaches that come with handling hazardous solvents. By adopting this dry process, manufacturers vastly lower their hazardous chemical exposure. And as global regulations continue to tighten around industrial chemicals, the early adopters of DBE are going to find themselves in a highly favorable market position.
Which leaves us with one incredibly provocative question to think about. Will traditional wet coating lines become stranded assets before 2030? Think about it. If the dry process scales as projected, delivering 80% lower energy demand, factories half the size, and total regulatory alignment, those legacy wet lines with their 50-meter ovens might quickly become obsolete relics. It's a fascinating pivot in industrial engineering, and for sure it's one that will dictate the winners and losers of the next decade of energy storage. Thanks for joining me for this explainer, and definitely keep your eyes on the factory floor.